Let's highlight some important points here. Obviously, water is important to life, to our planet. It covers roughly 2/3 of our planet, 71% almost. Our own body is 65% water. And the cytoplasm, the cytosol, is the liquid inside any cell. Is 70% of the cell's weight is water. So why is water such a big deal? We're going to find out. Okay, if you look at the water molecule, water is H2O. And here we have a structural formula of water with, looks like a ball of oxygen and 2 balls of hydrogen stuck into the ball of oxygen. Okay, remember these are covalent bonds between the hydrogen and the oxygen. So now, this is be learned in chemistry. Oxygen has a high electronegativity. You don't have to know that term. It just is greedier for electrons. Electronegativity means greediness for electrons. Okay, so oxygen is more greedy than hydrogen for these shared electrons. Remember, covalent bonds are electrons shared between the atoms. But yeah, they're sharing it, but oxygen is greedier. It pulls electrons more on its side than the hydrogens do. So that causes oxygen to be slightly or partially negative. That part of the molecule is partially negative. And the hydrogen ends of the molecule are partially positive. Why? Because oxygen is pulling electrons more towards its side, causing oxygen to become partially negative charged, not totally negative. He didn't steal the electrons. He just is sharing them more on his side than hydrogen's. And hydrogen is not getting electrons all the time in the bond, sharing them. So the hydrogen becomes slightly positive or partially positive. So water is called a polar molecule because it has, here's oxygen, here's the hydrogens. It has a slightly positive pole and a slightly negative pole, like the north and south pole, but not magnets. So this summarizes a polar molecule, a molecule that has polarity, has a slight difference in the charge on its different ends due to unequal sharing of electrons. The slightly negative end will be because that atom takes electrons more on his side than the slightly positive end. So the whole molecule is called a polar molecule. Okay, so the words are kind of technical here, but let me just explain. See the blue dotted lines between these slightly positive and slightly negative poles of the water molecules? These are called hydrogen bonds. They're not really strong unless you have a lot of them. A covalent bond is much stronger than a hydrogen bond. As these water molecules move around, the bonds break and re-break as a molecule water molecule moves away from one water molecule and towards another. Now, that would be in the liquid form. In the solid form, ice, of course, the molecules are just slightly vibrating instead of moving around quickly. So the hydrogen bonds are more stable. They're not breaking and re-breaking all the time if your water is in ice form. So hydrogen bonds are intermolecular bonds. I don't really like to call them bonds, but we do. Intermolecular means between the molecules. They're not inside the molecules. Okay, that would be a covalent bond. These are the covalent bonds. The dotted lines between the oxygen and the hydrogen are the hydrogen bonds. Okay? Now, hydrogen bonds can form between oxygen and, well, between hydrogen, of course, and not just oxygen, but also nitrogen. So molecules with fluorine, oxygen, or nitrogen in them, as that red ball in the picture, could hydrogen bond with other polar molecules. But we'll consider that later. Because of intermolecular bonding, hydrogen bonding, we got all kinds of important properties of water. Unique properties of water that are important to life. First of all, water is a universal solvent. It dissolves other polar or ionic substances. So like salt or sugar. Salt is an ionic substance. Sugar is a polar substance. And so water can dissolve those. Water can stick to other water molecules. That's called cohesion. Water can stick to other polar things or charged objects. So if it's not dissolving the polar substance because the molecules are so big, it can stick to them. The water can. Like water sticks to our skin or a window. That's called adhesion. Think of adhesive tape. It sticks to something else. Because the water's intermolecular attractions, because of the hydrogen bonding between the water molecules, it's difficult to change water from the liquid state into the vapor state. So it takes a lot of heat to make the molecules escape their hydrogen bonds and separate from each other. In other words, it takes a lot of heat energy to be absorbed by the water in order for it to evaporate. So that's an important property. That we use for sweating, for example. Sweating cools our body. So we excrete water through our sweat glands, and the water absorbs the heat of our body and evaporates, cooling our skin. because water sticks together. It has a high viscosity. Viscosity is a resistance to flow. Think of honey. Honey has a very high viscosity. Think of what maple syrup, high viscosity. Unless you heat it up, you remove some of those. I mean, you increase the speed of the molecules so they separate from each other, and it becomes less viscous. Okay, think of doing a cannonball in the swimming pool. It hurts because the water sticks together and resists something flowing through it. Also, it puts an upward force that keeps you buoyant or floating like a boat. Okay, so let's go into some details here. So, water is considered a universal solvent. It doesn't dissolve everything, it just dissolves a lot of things. Okay, anything that is polar and small molecules, I mean, not huge molecules, it will dissolve. Also, anything with ions, it will dissolve typically. Not anything, but most things. But it will not dissolve nonpolar substances like oils and fats. So when water dissolves like sugar, it forms a water sugar solution. A solution is just a mixture of a solvent, the fluid that's dissolving something, and the solute, the thing being dissolved. And even with a microscope, you can't see the individual particles. The solute or the solvent, they mix together. Okay, so here's a picture of an ionic compound in water. You can see the individual water molecules tearing apart at the positive end. The positive ends of the water molecule will form an attraction around the negative ion in the salt, and the positive, the negative, partially negative end will, of course, attract to the partially positive, the totally positive charge of the ion. This will tear the ions apart from the crystal. Okay, it will tear them apart, pull them apart. And that's what dissolving is about. Okay, things that are soluble or easily dissolving water are hydrophilic. Philic means loving, hydro means water. Things that don't dissolve in water are hydrophobic, water fearing or hating. Examples of that would be like oil, anything greasy, fat. So, because water is a universal solvent, it is very important as a mode of transport for things that dissolve. So, in animals, dissolved solutes are carried through our body, inside our blood vessels, in the blood. So not only these dissolved solutes are food molecules and gases like oxygen and carbon dioxide. So because these things dissolve in water, they're easily transported through the cell or through our body. Plants have vessels, vascular tissue vessels that carry the water and minerals and sugar molecules through them. So plants and animals rely on water as a transporter of important dissolved molecules and gases. So this picture is pretty funny. It shows when water molecules form hydrogen bonds with what other water molecules, we have cohesion. So see these two molecules kind of holding hands. That's the hydrogen bond. Okay, so that's called cohesion, company together, water sticking to itself. But then water also sticks to other non-water molecules. And that's called adhesion, like adhesive tape. So cohesion is really important for surface tension, whereas capillary action, which we'll talk about, is both cohesion, due to cohesion and adhesion. We'll talk about that now. Okay, so when a drop of water hits a surface that is not going to dissolve, it makes a drop, makes a plop, a drop like this. Now, where water hits the air, there's not water molecules all around these water molecules, just below it. And so these attractions are going to be stronger than these attractions because the water molecules don't have any other ones pulling them in all directions, just below it. So there's going to be kind of like a skin on the air-water interface. This forms like almost like a skin where the water is slightly more dense than the water below it. You all seen probably bugs that can walk on the water, like water striders. They can walk on the skin of the water. You can see that. You can even try floating a paper clip in a cup of water. If you're careful, it will happen. Okay, this is all due to the cohesion of water molecules. Okay, capillary action. If you ever gone to doctors and they've taken a drop of your blood to figure out what your blood type is, what they do is they puncture your thumb with a little hole. Then a drop of blood comes out. A droplet of blood. They squeeze your finger, and a drop of blood comes out. Then they put this really skinny straw into the drop. And that blood just sucks right up, like someone's sucking up the blood. It just climbs up that tube. So you'll see it go very quickly up the tube and then stop when it's all in the tube. This is called capillary action. Okay, so the skinnier the tube, the faster it will climb up. This is how plants take water from their roots all the way up through the stem to the leaves. Okay, capillary action. So you can see here that they're pointing out that the smaller the diameter of the tube, the faster the capillary action will happen. So this picture right here is pretty. The water molecules are way, 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 way too big, the little green balls. But anyway, this is showing the barrels that make up the xylem, the very skinny vessels that go from the roots up the stem to the leaves. Okay, what happens is the water molecules stick both to the walls of the vessel and to other water molecules behind them. And as they climb up the walls, they pull the water molecules behind them ahead, upwards. So the sticking of the water molecules to the wall is adhesion, the walls of the vessel, and the pulling up of the water molecules behind them is cohesion. So both of those are occurring with capillary action. Okay, there's holes in the leaves, little microscopic holes that let the water evaporate. As the water evaporates, they pull. That's the upward pull against gravity. That's pulling the water upwards from roots all the way to the leaves. So water molecules, like I said before, have to absorb a whole bunch of heat before changing its state. For example, from liquid water to water vapor. So why? Because you got to get those molecules moving fast enough to escape their hydrogen bonding that's holding them together. So if these are water molecules in liquid form with the hydrogen bonds, in order to shake them enough to escape, when you absorb heat, you move faster when you're a molecule. Sorry, you should know that. Okay, so the faster I make them move by heating them up, the more they can, more easily they can separate. But it takes a lot of heat to do that, to break those hydrogen bonds and to get them moving away from each other so that they're not affected so much by hydrogen bonding. It takes a lot of heat. So you learn about the specifics about that in chemistry, but right now, I'll just leave it at that. So, in us, we can, when we get hot, because we're doing a lot of exercise, we're getting heated up, what happens is our body tries to do homeostasis, thermal regulate, keep the temperature of the body constant. So it has to get rid of this heat, and to help us get rid of that heat faster, what happens is we have sweat glands that excrete water, and the heat from our skin that's building up, our body is building up, evaporates that water if it's not too humid outside, and takes the heat out of our body, cooling us. Okay, so the heat from our body is breaking the intermolecular bonds, the hydrogen bonding between the water drops, And as those water molecules escape as water vapor, it takes the heat with them, cooling our skin. If the air is really humid, this happens much slower, and so the water just drips off of us. Like in Florida, Florida's very humid most of the time. So we sweat, and the water drips off, not cooling us very effectively. Water is also a better heat conductor than air is, because it's denser. So it transfers heat quicker. So if you get wet, heat comes out of your body through the water quicker than it would through the air, the dry air. So this is why if you fall into the ocean on a cold day, you can go hypothermic very easily, because in minutes you can die or go unconscious because so much heat has left your body. Okay, in this picture on the right, you can see water. The molecules would be moving all over the place in liquid form on the bottom picture. And here's when the molecules slow down, they can form this organized hexagonal structure over and over again. You know, it repeats over and over again. So you got one like this, and one like this. Anyway, so the water molecules form this hexagonal kind of structure when it forms ice. So the point I'm trying to make is when it's forming the ice structure, there's lots more space between the water molecules. So in the solid form, ice form, it's less dense. More space between the water molecules. So ice is lighter than water. I shouldn't say lighter. It's less dense than water. Less dense than water. And it will therefore float. Very important, because floating ice in the wintertime, the ice forms, and it's because there's so much space between the water molecules, it forms a good insulator. So heat doesn't get through ice very quickly. So that's why fish don't die during the winter, because the ice covering of a lake will keep the fish underneath warm. Same thing when you build an igloo out of ice blocks or snow blocks. You can live in that and not freeze, because the ice blocks form a good insulator.